All right, everybody, let's take a look. Let's hope this one works. Let me get this up and projecting. Okay. All right. So, sorry, it's been a little bit. Sorry again for the delay and the weirdness. But I was glad to see some different conversations on the Slack. It was kind of an interesting week and a half for you guys. Let me go back through some of these in case there's any questions I didn't get to. I replied to a few of these. I thought it was funny that Mary misplaced where her design of everyday things are. I think I've loaned out like 4 of them. And that's funny that Stefan was the one who got it. Yeah, it seems like you all really kind of latched on to some of the sensory stuff and the memory things, which is really good because you will need it more as we get into this section. It should make more sense as we start to see this. And I saw the comments about asking for the slides. Yeah, I should be able to put them somewhere. I guess post in the Slack if there's a place that's easiest for you guys. I can put them on Blackboard, but if that's what you prefer, we can do that. Or a OneDrive folder or a Google Drive folder might work. Just kind of let me know whatever you prefer. Midterm questions. So I've had one-on-one conversations with a few of you about the midterm, and then saw some other questions in the chat. So a few of the things I want you to take away from it, and this might seem kind of abnormal a little bit, I guess, to other courses. And I guess that's also kind of intentional. So the first thing I'll tell you is try not to stress out about it. Especially this time in our lives, we all kind of have enough stress. So don't let this add to it. Like, I'm reasonable. So if there's something comes up or whatever, just let me know. Or if you have a different idea of something you want to do that might be easier for you and still kind of get the same value out of it, that's fine with me. So, reach out for questions, find something interesting. That is the biggest thing I can tell you, is to find a topic that interests you. Those of you that have been through these various design projects, redesign a can opener style challenges through your masters or whatever, go outside the box. I mean, you don't have to do a full design project if you want to. You can analyze an information architecture or look into some different stuff. And if you're really stuck, reach out and I can help you brainstorm some ideas. And then just remember, whatever you end up doing, you will need to post on Slack. And in terms of what you will do, like I said, I'm pretty open. I've talked with some students about a redesign project where you would redesign something, get user feedback, kind of go through the regular loop and everything of a design project, and then report on it through a PowerPoint or something. That's an option. You could also do essentially like a research project where you dig into a topic and just kind of highlight the pros and cons of different designs related to nuclear, those kind of things. And you can do that in a presentation if you want. You can also write a paper. That's something, the reason for the kind of like these menu items is some people don't like to do presentations. Some people prefer to write papers. And, at this point, we've got a few PhD students in the class, and people from different application spaces. Writing is probably the most important ability you need in human factors. So if that's something you want to do, let me know. And if you're worried about, are you on the right track or whatever, you can send me early drafts or we can talk about it, kind of whatever you want to do there. I got asked a little bit about length for papers, which this probably isn't a satisfying answer if you tend to, really like things in black and white. But I won't really have length requirements. Like I mentioned in the initial lecture, my background is in philosophy, and for 4 years I wrote 2 to 4 papers a class, and with I never had a length requirement. My professors used to always say, um, you you know, there's probably a minimum that you need to cover this topic in depth and in a valuable way. Um, but the maximum is really kind of what we want to read. So I'd say most topics you probably need at least 5 or 6 pages to really cover. Think of it like a conference paper length or something, but it can be a little bit longer. And you can also do a mix of some of these if you want. So, you know, try to get creative about it. It's almost I thought about this before the course, and I almost wanted some of these to be a design project in and of themselves. So you're almost trying to design your own grading mechanism. And so you guys, you all probably know what way you learn the best in those things. And I want you to take advantage of that. That's also why I didn't force everybody into groups. I never liked group projects, but they can be valuable, and you do need to be able to work in groups. So that might be something we look at later in the course or something, but I didn't want to do that initially. So hopefully that answers some general questions. I still want to either talk with you and go over things, or just let me know what you're planning on doing so that I know what to expect, and then if I can be of any help. So I think we have, you know, we've got a decent amount of human factors uh, or human factors trained, or at least psych experienced people in the class, but not so much nuke experience. So um, if I can be of any help guiding you there, that's an area I can be pretty useful for. So, okay. This lecture is going to be a lot. So it's about twice the length probably of the other one. So feel free to pause. Don't worry about trying to crank through it all at once. And yeah, I'm going to get the slides out so you guys can start having those if you need them. And yeah, that's just try to keep up with nuclear. What I'll tell you is they love their acronyms. So you'll see a lot of those. And try to remember that nuclear was born from the nuclear navy. The nuclear nuke power came from there. So that's another reason of some of the acronyms, some of the stringent phrasing and precise terminology and stuff is some of that militaristic influence coming in. What I would strongly recommend, and I did this when I originally started at the INL, keep a little pad open or something and write down anything that I say or that you read that does not make sense. If it's something that's not defined, I couldn't define everything that's in this, twice the size it already is. But if there is anything that you have questions on, write it down and ask, because it will make the rest of this so much easier for you if you understand some of those terms and how they fit. And sometimes a simple definition isn't enough. So this week, actually, depending on how fast we get through this, what I'll probably do, I usually recap the Slacks at the beginning of the lectures. I'll probably recap any of those questions that I get or that I see in the Slack, or if you want to email them to me or whatever, just so if you didn't get a chance to get your question answered or it needs a little bit more context, I can give that to you. But yeah, just try to do that. And if you end up with a list of 40 different terms, send them off. We'll get them answered. It's better to do that than not. All right, so now we'll head into the meat of it all. So this is primarily going to be me checking you into the deep end of the pool on methods, evaluation, standards, and anything else around that. So the first thing I want you to think about is, why are standards important? Standards are a huge part of nuclear and all process control, anything with high consequence safety critical processes. the two main standards we deal with in nuclear is 0711 or 0700. That's usually how you'll hear them referred to. And you'll see pieces of these as we go through. This lecture, you'll see a lot more of 0711. 0700 we'll get into more when we get into the design components. 0711 is essentially the test that you have to pass if you're going to design a nuclear system that the NRC has authority over. They're going to be grading you based on 0711. So this is an interesting link on why standards are important if you are interested in more information. The biggest reason that we use them in nuclear is because every step needs to be documented why we did what we did in case there's ever an accident. In past decades, there's a lot of focus on, okay, who's to blame. That is less so now in terms of root cause analysis and the way that those are usually done. But if we don't have an accurate timeline or really like life cycle of how these decisions were made, then we can't go back in and make it better. We can just make assumptions and fix that. So that's another big reason that we have standards, because then we have something to point at and say, this is why we did what we did, and now it needs changed or it needs updated or anything like that. It also gives us something to point at that's outside of organizational things, whether it's organizational pressure, political pressure within groups, economic pressure, those kind of things. There are reasons we can say, no, we can't do that because of standard X, Y, and Z to give us some cover there. That's another common use of these. These are just kind of some examples. This isn't anything to memorize. Like I said, the two big ones you need to be aware of are there. But you'll see these sometimes referenced in nuclear documents. And it's important to just kind of know that there's more than two. So I would say of the ones in here that we see the most, the two big new regs that are bolded there, and then the MIL standard down almost to the bottom there. The MIL standard usually will include a lot of ergonomic and anthropometric guidelines that we have to use. So, but the ISOs, the IEEEs, they're useful, valuable. They have there's a lot of overlapping information, but sometimes different perspectives can help there. Okay, so now we're going into kind of what these methods will be. I think some of you will actually enjoy this because I got several questions about task analysis, just kind of hey, are we ever going to get like a how-to? Because I know that you didn't get it during your master's. And so this will probably be the closer part we get into there. And that's an example. That could be something you want to do for a midterm. Task analysis is a pain and is, at least to me, and can be very granular, super, super useful and valuable, but can be a lot of work. So if you want to do a task analysis, something just so you can get that under your belt, great. Sure, we can do that. So let's go in here. So here's this awful Olympic person. I still hate this characterization of human factors in ergonomics, but it tends to work and people recognize it. So just remember that we're looking at both capturing and understanding human performance in various situations, and we're trying to design situations to optimize our human performance. Okay. So human factors helps design and validate technologies. And what does that mean? That means that we're essentially in a constant circle of gathering or applying and gathering knowledge, or gathering and applying knowledge. Kind of depends on where you are in the circle. So when we look at applying knowledge, we're looking for good practices along design principles, what makes it work and what's been tested and tried. We try not to reinvent the wheel as much as possible. So those properties of a good HSI, those have been tested. That doesn't mean you may not have a novel idea. It just means, it might take a little bit more testing to topple an existing paradigm. And we feed into these design process with design requirements, which we'll get into a little bit more for a lot of the rest of the class. But gathering knowledge is important as we look into each HSI has different characteristics for different things. And understanding that within the angle or context you're looking at is really important when you're going to be designing something. And that second one, capturing the human use of technology, is really important. Understanding not just how the system works, how does it fit into the broader world of your users? That is also very, very important there. So the V model, this helped me make a lot of sense of some of this characteristics. So the other thing I've said a lot, remember, none of this is gospel. It all could be wrong for whatever situation you're looking at. These are just guidelines. So the V model essentially links between what you do and how you validate that you did it well, or how you validate that you're in the right spot. So when you come up with your requirements, when you go into acceptance testing, you will find out if you got the right requirements. Your users will be able to tell you, or they will fail miserably. And it breaks down, all of these from really base detail to high level, and then kind of this timeline of build versus validation. Iterative design is really important in all design things. You should never go with your first design. That's never going to usually find any success for you. Also, you should never be the only person trying to design things. We are too weak to our cognitive biases to let that happen. So when we're talking about this, and you'll see this term system engineering sporadically, it's important to remember what we're doing here is designing human systems. So we are doing human system engineering. And so some of the system engineering principles from mechanical or other fields you might find useful. What we're focusing on in this and in this slide too is user-centered design or human-centered design. So we are essentially in this loop of gathering knowledge, analyzing it, designing from that knowledge, and then testing those designs, which is essentially a way of testing assumptions. And then we go back, and what we learn from that design becomes a part of our gather knowledge step. So that then enters the loop over and over again. And over time, it should give us a sense of precision and really narrow down where we're at and why our design works or doesn't work. And hopefully you find less design issues as you go forward each time. Hit the wrong button. Yeah, so we talked about this. So this is within the applying gathering knowledge steps. I also think it's important to realize 0711 is also evaluating your knowledge. That is a key part of 0711. And it is how, and it's even beyond, 0711 isn't necessarily judging your results. The NRC is judging the way you got to the results, which is important to remember. And 0700 is it's a style guide, primarily, one that has a lot of very good recommendations on things like color, legibility, interactions, dynamic natures of your systems. Really, really useful, just humongous, things like an encyclopedia. So, so definitely something we go to when we need to get some answers on something. Methods versus measures. So this is an important one. This is one of those weird distinctions that you will get a lot of in this lecture. So methods are primarily outlining how you apply or gather knowledge. And they're going to be techniques and the process essentially that we follow as we're going through it. Measures outline what the result knowledge is. So measures are so we know how we're going to gather knowledge. We're going to go talk to 100 people. The measures are, what are we going to ask them to get that knowledge? And how do we how do we collect that information from them? That's what's the primary difference. So methods include measures, but not usually the other way around. Somewhat, at least in the realm that we're talking about here. So here's a common example. What's the ideal input device if you're going to be working on a control board? And these are just some examples. So for applying knowledge, how do we know, or what do we know from what's been done before? So these are some assumptions or pieces of information that we have gathered. Many digital systems predate current input device technologies. That's true. The vast majority of nuclear control rooms that you will or could possibly experience do predate the mouse in the way we understand it now, and GUI-based graphical user interface operating systems too. So it's not applicable to generalize our current understandings of these methods, or not methods in that sense, but of these tools or input devices to generalize backward. It's not going to be helpful. Surrogate systems like aviation decided against touchscreens because of turbulence. Well, hopefully your control room doesn't have turbulence, or you might have a bigger problem. So that one's not very applicable either. Gorilla arm syndrome. The arms get fatigued using a vertical touchscreen because you have to hold your hand up too much. It's applicable, but it might not be enough to help you design something given your situation. So what's the solution there? We get into a situation where we can actually get real operators that currently use the system that you are looking at to play around with a prototype and to get some information on it and to get them to talk with you about their experiences with it and what they think. And from this is actually an example of a real life situation we did. You know, design recommendation was mouse because operator performance was the best. They made the least number of mistakes versus what they preferred, because the precision is the priority in nuclear operations. Now, in some other like digital design, the preference might be king, but in nuclear, it's the precision and efficiency. Human factors methods per NUREG 0711. Okay, so one thing I'm just gonna stop here for a second as you look at this. NUREG 0711 doesn't have a table like this. This is a result of trying to fit design tasking within an 0711 framework. So, and the idea there was, okay, if we do designs and if we do design tasks and they fit in these boxes, then we have some, it's easier to support us when we go to an 0711 evaluation and say, look what we did, and look, these ones fit in these boxes. So we did do every step. And you'll see that throughout this. A lot of nuclear design up until this point has been a build your own adventure with an eye on 0711. So this will be one thing I want you to think about as we're going through that has some concerns with that, especially if it sets your goals counter to each other. So is your goal to make a good design regardless of whatever checklist you have to do, or is your goal to pass the checklist so that you can actually get something implemented? And up until that point, they were somewhat at odds. So, but this is where it really gets interesting here. Even though they weren't intending to, I don't think, the writers of 0711 clearly had certain system engineering and design engineering principles in mind. So the V model is present there, as is our iterative design loops. So as you can see there, there's a lot of overlap with just common design thoughts or ideas that and what 0711 is judging. So it's an interesting, I guess, coincidence, or one of the strange things that, when you see things that come together even though they weren't intended to, it just happens that way. So now we're going to get into the primary four methods that you will hear a lot of in nuclear. And each of these methods are designed to answer specific questions. So an operating experience review, you're looking at past successes and failures, different improvements, lessons learned, those kind of characteristics. Function allocation and requirements analysis, which isn't listed there, will help you identify what's the role of automation or mechanization in your plant, and identify either obvious opportunities to improve that or help give you some questions that you can ask. Task analysis, this is what you really need to undergo to be able to understand what you're designing for. So what is the goal of your users as they go through this performing this task? It also will help kind of lay out what requirements you're going to hold them to, and not them, you're going to hold the system to. So the system has to support their actions in various ways. So how are you going to support that in the design? Verification and validation. This is the boogeyman. Sometimes you'll hear it called V&V in nuclear. This is the last stop on the line there. Does it work? You made all these claims that it was super safe and efficient. Are any of those true? Are there any issues we can come up with to sink you? So these are the main and big ones that we have to consider. Operating experience review. So like I said, operating experience review is primarily focused on past or predecessor designs. And the idea here is to understand the lessons learned and just to avoid any mistakes of the past. This also helps because you can't really, for systems as complex as ones in nuclear power, you can't really just jump in and start designing. There's a lot of technical debt and history and just operational experience, no pun intended here, that's really important to understanding what is going on in the system and why it is the way it is. That's really, really important. We've all used a system that, or a process or something that had a weird step in it that didn't seem to make sense until you ask, and then, oh, we do that for this one very, very specific purpose, but it's worth the extra cruft or whatever, because it prevents any horrible side effects that could happen otherwise. Now from, so that second paragraph there, from an 0711 perspective or a regulator perspective, the focus is on making sure that these people that are designing something in a nuclear power station did their due diligence, and that they respected the past and they're not going to make the same mistakes. And as this is kind of, we'll go through this with each one of them. The idea, and I explained this a little bit in the past, we want to come up with the second bullet here, a literature review of problems with the HSI. And that plugs into this results summary report or an RSR. It also can plug into design requirements and everything else. It's essentially regardless of what acronym report they want to call it, you are trying to pull out issues that your design needs to solve. And this covers some more of those aspects in step one. Step 2 is another, the kind of next layer out that we'll do in nuclear, where we'll go out to industry human factors issues. So, for example, your plant may or system may not have had this specific issue, but another facility did. And so, one of the big things in nuclear is we try to share lessons learned, we try to share issues and accidents that happen so that we can learn as a community. Um, and these are just some of the ways that you can get that information. Most of these are not publicly available. You would definitely have to be in a position where you would be granted access to them, but there might be some pieces of this. This is also now, this may be easier in situations involving transportation. So if you're looking at essentially this same path, but you want to do trains or aviation or some of those things, also a fair amount is not public, but any reasonably large incident will have a NTSB report, and those are often public. So keep those things in mind there if you need to search for more information. So step 3, this is really important to collect, okay, what kind of technologies are we looking at? And what kind of, this is a twofold question. This is what kind of technologies are possible in our situation, and what technologies may we want to use. Maybe our operators, this references computer-based procedures. Maybe our operators went out to a conference or to a trade show and tested some specific software thing that they really liked and think it could be useful. Having all those pieces will help you, again, not try to remake the wheel. If there are some of those easy wins you can get, they're valuable. The last step in an second to last step in an operating experience review is to interview plant personnel. This is something you'll see really common in basically every step of everything we do. Talk to people. Talk to people who know what's going on. So this lists operators who have experience with the human system interface. You can also talk to other people. You can talk to facility managers or kind of anybody that is adjacently related. I've always, as long as you don't fall down rabbit holes or get focused on a wild goose chase, more information doesn't hurt. So, try to be aware of that. Another thing to consider are beyond normal incidences. So, nuclear power has been around for decades. You're not going to find a ton of non-degraded systems out there, or non-degraded parts or equipment that maybe doesn't quite run the way it did in 1975. So what does that mean for the performance of this human system interface? It's not uncommon that we can develop sensors that are more sensitive than the pump was ever built for. And so at that point, it's just noise. Those are things to consider here. And what happens with alarms, displays, controls, operator aids, communications, and procedures. All of this is part of the operating experience review. It's not just focused on the display. We're looking at the experience of operating the facility. Step 5, so important human actions. This is another very common nuclear term, and it has a very specific definition. So if you have any questions on this, make sure to ask. An important human action is any action that could impact the safety of the plant. So this second bullet here risks significant human failure events from the PRA and HRA. So PRA and HRA are analysis tools that are and tasks that are undertaken as the plant is being designed or the systems being designed. And they both result in some key human actions. So, okay, at this point, if if we're in X situation, Bob has to hold this lever at this time. That's an important human action. And they can identify that because if those actions don't happen, we see an increase in the probability of negative effects on the plant. FSARs and DCDs will also have them. Again, those two are especially things you're not going to have access to unless you're internal. But it's important to know that things like that exist. Important human actions are generally known, that they're not secret or things that we're trying to hide. They're in every single system. So what does that mean for us? We need to understand what scenarios have these important human actions, because those scenarios are going to be very important for our user testing of our design. What performance issues are they concerned about? Is this a time issue? You have to do it so fast, or is it a vigilance problem? What's going on there? And then how can our new design prevent the errors? So the best thing we can do with a new design is remove important human actions. We definitely don't want important human actions if we can avoid them. We want humans in the loop, but we don't want humans to be the linchpin if we can possibly avoid it. So these are common examples of what you may do, or different write-ups that you might see the operator versus the objective problem, and then how other industries you might be pulling that in. I'll leave this up for a second in case you want to read them. These aren't necessarily relevant situations for anything, they're just examples. All right. So next, applying knowledge. So once you've gathered everything, we have to document our process and the sources, findings, and design decisions. If you haven't noticed, you're going to be writing a lot in nuclear design. Everything needs a source, and everything has to be clear how we went from step to step. It's very useful to use a tracking system to tabulate these. So Excel is really useful, or if you have a different specific thing you want to use, Trello or whatnot, you can give it a shot and see. So yeah, some identified issues may be carried forward in the design while a solution is determined. A lot of them will. If your design brings about a new important human action that could have a really high levels of consequence on the system if they're not done correctly, those might be things that you need to change about your design before you even get started. Nuclear is definitely not looking for any new ways to fail. I like this third bullet here. OER can seem really focused on what's wrong and what's negative and what was bad about different things, but it's important to catch the things that they like and the things that are good. The system used to do X, Y, and Z. We changed this, now it works in this way, and it's never been better. Those type of information, or that type of information, is incredibly important for as we move forward. Not just in, hey, let's make sure we include some of these good design elements, but remember your users have used this system for a long time probably, so consistency is also important. If we go back to those, the memory sections, if you have something that's well rehearsed, you're going to retrieve it more accurately and faster. So if we can keep as much as possible in the process or the design or those things, that's really important. And then OER should result in some design requirements for the HSI. You find almost all of these should result in some design requirements. Okay, the next one, function requirements analysis and function allocation. You'll hear this called FRA or FA sometimes. Sometimes they'll use one of the two acronyms to include both of them. I wish it made more sense. So we've got the definition here from NUREG. Essentially what we're talking about here is an understanding of the plant, of the human, an understanding of the plant functions that have to be undertaken. And then from there, we take the step to, are they automatic or human operated? So functional requirements analysis identifies plant functions that must be performed to satisfy the plant's overall operating and safety objectives and goals. So this is going to be your initial cut set of, these are all the things that we have to do for this plant. You have to be able to turn up power, turn down power, all these different functions. Function allocation is the next step, which says, okay, we know we have to do this. Are we going to have people do it, automatic systems, or some middle combination? When we talk about automation, there's two primary types: control automation or information automation. Control automation is mainly going to be, we're looking at reduced staffing, reduced training requirements. This is definitely, control automation is going to be present anytime you're asking a human to do something they can't do. Like, oh, you have to respond in 2 milliseconds, or you have to respond every single time without fail. Those are task descriptions that are more suited for automated systems. Information automation are kind of contextualizing situations and data in a way that helps the operators perform their tasks. So looking at overview screens are an example of information automation. The system's not necessarily doing a bunch of algorithmic transformations on the data. It's just maybe filtering or doing various things on the back end so that you don't get 15 pages of data when you only need 2 lines. That's the key aspect for information automation. Automation can be both mechanical and digital. Most safety systems in nuclear are a mix of both. And you will see, this is one of the things as we start looking at digitization of nuclear control rooms. The opportunity for automation is really high and somewhat needed. Nuclear power is in a somewhat precarious economic position and could use some efficiencies, and not a lot more efficient than just a computer that turns the button on and off every single time without fail. Here's some example of definitions of automation. So the sensing of environmental variables with artificial sensors, data processing and decision making, mechanical actions are all examples of automation. It's specifically using a machine to augment or replace activities normally performed by humans. This can take place in nearly any form. Automation in nuclear specifically is still extremely new. There's a lot of use cases to explore there. So human automation crosswalk, this is an example of various things we'll ask the person to do and then what an automated system would do to kind of measure that, or not measure, match that, sorry. Now we get into my favorite acronym of my entire life, which is HABA-MABA, which is humans are better at, machines are better at. It originally, if I remember right, was MABA-MABA because I think it was men are better at, and it has since been changed. I don't recall. So machines are catching up. So anything that has an asterisk are things where humans were better at before, and they might be getting challenged by machines now. Human performance in a lot of these fields is mostly peaked. We're not seeing any additional increases in human ability. But in general, the green ones are ones that we know humans are still better at in these situations than machines. And any of them with the asterisks, they're still probably better than the machines, but it definitely depends on the situation. And then things that machines are better at. The green ones, like before, are ones that almost certainly they are better at than humans. And the other ones are situation where it depends on the context that what you're looking at. What we're talking about here is function allocation. There's also a part down here at the bottom, teaming. So human automation integration or collaboration is a huge focus, and it's only getting bigger in systems design, especially in nuclear. And we'll go into that in a little bit more, but it is an important topic. So function allocation analysis, it is not a just binary yes, no. It very much depends on where you rank things in here. I would say most things end up in 3, 1, or somewhere in 5. That's the vast majority of the things that you'll see. It's usually pretty cut and dry if it should be automated. And where we get involved is obviously in region 1, because we're not designing interactions or displays or whatnot for systems to perceive. We're designing that for humans. Also, though, keep in mind this big center area here. What do we do when we have to design something that's partially automated? That's a huge aspect for design tasking, and that's a hard problem to solve. Here's some example automation. So safety systems, they are both, and this is broken down by both control automation and information automation. So control automation, you have automatic reactor trip systems. They are still mechanical in the United States. They are digital in most other foreign territories. They're engineered safety systems that are relying on things outside of the control room to ensure that the reactor core can stay safe. Non-safety systems, you'll see computer-based procedures might be able to exert control over various systems depending on what you do. Really, any series of steps like this automatic turbine startup is a control automation. You're giving it instruction, but then it is going forward and taking the steps for you instead of you having to manually do them. Information automation, these are some examples. Automatic calculations is a big one. There are a lot of operators still that remember when they would have to break out tables or go to their shift technical advisor, they would have to recalculate different values throughout the plant. And that is a concern. Depends on the plant, but usually I think reactivity, just as a concept, is an abstracted calculation. Reactivity isn't a thing we can objectively measure with one sensor. So it's actually a mathematical formula that we undergo in the displays in order to show that. So they used to have to do a lot of that by hand. Oh, and here's an example of function allocation between personnel and automation. These type of tables are very common, and you'll see them in a lot of these, this type of work or these type of tasks that you'll undergo. And keep in mind, any of these assessments need to be accompanied by some explanation of why one or the other, so that that can be kind of negotiated or examined if needed. Here's an example for some information automation. So this is from an operator in loop study done here at INL about visual dwell times captured through operator tracking. So there's 3 examples here. The top one is a fully automated or analog control board. The middle is digital DCS HMI upgrade. So this is prior to any kind of an information automation or overview display, which is the bottom. And so what do you notice here? Well, in the analog, they're scanning and they're spending pretty consistently the same amount of time on the ones of interest that they're looking at. The middle one, that new window, totally consumed almost all of their visual attention, which is a problem if there's anything outside of that window that they need to be watching. There's a really big concern with tunneling, is what we call it, where you just get trapped looking at one thing. The bottom of DCS HMI with information overview display, we're a little bit more distributed. And so the question there is, okay, which one's the best? the top one's interesting to me because they spend a lot of time throughout each sensor, or not sensor, but instrument. So maybe it's a little bit more thorough. The middle one's obviously a problem, risk for tunneling. What if you missed designing a key task into that main display? It might get missed, those things. The bottom shows a good distribution of across the board, possibly still some additional focus though, or tunneling going on. We need more testing to validate that. So this is a breakdown of like FRA to FA. So FRA is definitely in the gathering knowledge world, FA is in applying. This is essentially how we would break that down. You know, we'd explore the information and interview people about what they want to do with automation. And then when we go to apply, we're actually looking at what can be, what should be, and then what kind of performance we're looking at there. So key processes, so these are the primary, you could almost consider them important actions, even beyond human actions. So yeah, there's usually going to be overlap with a PRA or an HRA. So these are kind of general characteristics of what a system should do. So these are important to think about because they're a little bit bigger picture, right? Than, oh, we need to design it so that we can open up different valves at different times. Okay, but what are you really trying to do? Like, what's the goal of this design? It's to produce power, maintain the heat sink, those characteristics of a safe functioning system. So those kind of taking that step back is really useful for design to make sure that you're not missing the forest for the trees, which is very easy to do when you're designing things. It is not uncommon to find that there's a specific element that you really get excited about and think it's going to be the greatest thing ever, and it ends up consuming too much of your time. So try to keep these big, high-level key processes in mind. So when you're questioning automation, is it essential? In my experience, most automation, or I would say most systems, have some essential automation. And these are examples of where we would say yes. If it has to be performed very rapidly, precision beyond human capabilities, requires greater human reliability than is available. So this is something you'd get from an HRA. And this is when it's not possible to automate, you increase staffing or build safety systems that can reduce single point failures. So this is where you might separate that function across different people, involve required checkoffs, those kind of things, so that hopefully you're preventing an issue if it was going to occur. And then is automation desirable? So this is mainly around, does automation help the operator's user experience of the plant, essentially? So is it easier for computers to do it? Does it require any fatiguing actions or boring actions? Especially anything around vigilance. If you just have to sit and watch something for a really long time, you are going to get blind to anything that would change if you get really bored, and then you're going to miss possible deviation that you needed to catch. So these are examples of areas where if you can automate, it's usually beneficial too. And the last one here is human involvement essential. So this is an interesting one to look at. You have to have people involved. If it is a core human responsibility, yes, you do. If you have to, the computers are still not great at communicating, and you'll need some precise ability to go back and forth in an emergency. Automatic response is difficult. So if you can't automate something in the control logic, that is a very common thing you'll run into. These plants, again, were built before computers were, in our pockets. They just, the control logics might not allow for automation in the way you're thinking. Personnel must remain in the loop. This can be, if you have a need to take over control or be involved for other tasks, you can automate this, but you still need to have them aware of what you're doing so they know when to actuate their part. So these are really important characteristics to think about. So how does function allocation inform design? It's going to essentially develop your entire ConOps. So that's another term you're going to hear a lot. It's concept of operations. Think about it as the philosophy for operating the plant. This is what type of systems do you need? What are your staffing levels, information or IT requirements, technical requirements beyond that? What procedures do you have and need? What's your alarm posture? These all come through in a function allocation, as do a lot of, okay, if this is going to be automated, how do you design that for the user? What about any tasks you're giving to the user? It helps feed into that eventual design requirement document. Thing to keep in mind for human automation teaming, Nuclear in general is highly skeptical of smart assistants. So anytime you hear smart being attached to something, you'll get a lot of raised eyebrows. AI is somewhat of a bad word in nuclear, not for bad reason, obviously, with situations like Twitter bots that go on racist rampages. But try to think about this when you're designing an automated system. How does the system communicate with its user? Because at that point it has to. It's taking actions on its own. How does it let them know what it's doing? We talked a little bit about three-way communication earlier in the class. What does three-way communication look like for a system? What about confusion? What about if the automated system doesn't know what to do? How does it explain that to the person? Failure. What if it can't do what it needs to do? And even if everything works great, how is the human going to have transparency into what's going on? Because they need to have that. That's where explainable AI comes in, or human automation teaming, all these. And try to keep in mind that in nuclear, operators are accountable for how these things are going to perform. Task analysis. So here's the fun part, right? Okay. Task analysis is designed to break out any task that you're focused on into the subtasks and specific contextual situations that that task will happen with. So you're going to be trying to identify human activities in a task. It's easy to think of it like steps in a procedure of human action or a recipe. So what, is there an order of operations to what you do? How do we get to that end goal given where we start? You can have different levels of task decomposition. So you can go everything high level, you can go down low. Functional system goals are starting points. And then from there, you can break out, okay, what human tasks are necessary to achieve that system goal. Okay, the steps. You're going to capture each major decision or decision action in a sequence of human and hardware activities. Yep, task analysis isn't just people. You have to capture what the system's doing too. Can almost always be done at a higher or lower level. Make the best judgment call for your specific application. There's no necessarily right or wrong way to do a task analysis, but you can definitely do one that is too granular or one that's too big picture. It is definitely somewhat nuanced. The main things you need to capture: who's doing whatever your task is, what system is affected, what plant function is accomplished, what's your goal. Two main ways to do it that are common in nuclear are hierarchical and tabular task analysis, which now we're going to go through the reverse way that I said it. Tabular task analysis. This is closest to a recipe. You are literally breaking out which specific steps and in an order of what would happen. So it's a little bit more cumbersome, time consuming. Useful if there's some disagreement or lack of clarity about what's going on, to really get down to what are the components involved here. For design, keep in mind as you look at this, what's important for our design. Time required, I could see being important. If you have to take a step pretty fast, you need to be able to communicate that and be able to give them a fast way to do it. Those are different aspects there. Hierarchical, a little bit messier, but makes more sense to me. But again, there's no right or wrong way. So hierarchical task analysis is like this top one right there. Maintain normal system operations. Okay, what tasks do you have to do for that? You break out those tasks, and then you break out the tasks below that. And obviously you can get pretty far down. Where you cut off is really a judgment call based off of your needs to do that. There are so many different types of task analysis, but just try not to get too caught up with them. They're just different angles or focus points on what is your operator doing. That's all they're doing. You've got a person there. What are they doing? That's all they're asking. So there are some that are more useful for others, but again, there's no real right or wrong way to do it. So what tasks are performed, who performs them, what systems are affected? This turns into, okay, input into the design of the system. What tasks am I going to have to support in my system? What information and controls are needed at the same time? It's really, really obnoxious and can be a really big safety problem in a nuclear system if you're constantly having to bounce between tabs to get this answer. What about people? How many people are required to perform the task? What staffing level do you need? What are the procedure steps? How are you going to train or explain to your user the things that have to be done? Remember, task analysis often occurs prior to procedure creation. It's usually an input to that step. So a lot of times you're working with system engineers or different SMEs on the systems to figure out what somebody has to do to make sure it's okay. Verification and validation. So this is V&V. This is the boogeyman. So the top one's definitional if you need it. The bottom one's the easiest way to understand. Verification is you're comparing a design to something. Requirements and standards by human factors expert would be expert review. What if you're comparing a design to a paper standard like New Reg 0700? That's verification. You're trying to verify that claims or characteristics of a design match something or line up with it or in agreement with it. Validation is proving it. So you can say my design satisfies standard XYZ because it does these 5 things under this time scale, therefore it's super safe. Validation is when you go and you put an operator in that seat and demonstrate that. That's the easiest way to understand these. So yeah, this is a way of explaining that word down at the bottom, integrated system validation, ISV is another one that you will see that sometimes will get people a little bit antsy. And that is because ISV is the step where the regulator puts your operators through tests to see if your design was up to snuff. So when we're trying to do V&V, we need a sampling of operational conditions. These have to be representative scenarios. This is where it's important to understand, why we look at 0711 at the beginning, because it's kind of like the answer key to a test. So we want to look at plant conditions beyond just normal. Degraded, transient, accident, shutdown, and reasonable beyond design basis scenarios. And I'm defining BDB because it is something that I never can understand. So Beyond design basis means accidents that take place in situations outside of its design limits. Plants are designed to be able to have a various number of things go wrong. Beyond design basis are an earthquake, hurricane, tsunami. Oh, these things aren't supposed to go wrong, but they do. They're taken into consideration in terms of probabilistically what's the likelihood these things are going to happen, and then we need to be able to answer some of these in a design and make sure our design doesn't just hamper or make it impossible to respond to such an issue or circumstance. Personnel tasks, so we'll need to know what important human actions are there. If you design something and you can't support an important human action, that's a problem. Different safety actuations. Are you monitoring the right things? Can you monitor the right things? All of these are really, really critical there. Context, high and varying workload situations, fatigue, degraded environmental situations. Sorry, the bottom there was cut off. So these are examples of not positive situations that you have to be able to design for. So expert review is the most common verification tool we use. So this, if we're doing an HSI expert review, we're going to be looking at computer-based control, different display technologies. Are they being used appropriately? What about the type of information display characteristics you're doing? Are the dialogue types good? Are they legible? Are the visualizations you're using, the actual charts, good? Are they well tested and they communicate the information you're trying to do that? Are they not pie charts, for example? Control characteristics, physical locations, and what personnel are using the system. Did you use a diverse set of people, shapes, sizes, etc., to design your system so that you don't end up in a problem where somebody can't use your system because they're not tall enough or whatnot? Task support verification. So did you do the task analysis and then did you design the tasks that you have to support? Are they considered in your design? And then does the human system interface conform to standards or guides like NUREGO 700? Validation, so ISV. This is performance-based tests to see if your operators can perform pursuant to the guidelines that they need to maintain safety standards. So these are representative scenarios using full crews, and we're validating all of these things. We're checking everything that you just evaluated or you just looked at in verification. Okay, you said that they were great. Now we're going to prove it. And we're going to see if when the rubber meets the road, do people actually perform well in this instance? And as you can see, this is another area where the methods and measures delineation can pop up. Human engineering discrepancies. So this is after validation or V&V tasking, a list of issues and how they're dispositioned. So did you correct it? And then how? You improved the design, process, procedure, you automated something, etc., etc. It's not corrected. Why not? These are really common issues that you'll see and why HUDs will persist. It's an artifact of the test. The simulator just broke or something. So it's not representative of what's going to happen at implementation. It's not a critical malfunction. That's when you usually have to back up pretty good. Or you're looking for a waiver. Waivers are a lot more common with these older systems that cannot be retrofitted without extreme cost expenditures, capital expenditures to get it across the finish line. So back to the process here, we're looking at expert reviews and user studies, and then we will pass that. If we pass the design, we can proceed with implementation, identify varying HUDs, and then make a plan of action to fix those prior to when you're fully implemented. I'll go through these last few slides and then I actually have to hop off to a meeting, but I have a little bit left that I'll try to get on as a second lecture later. I'll at least get this one. So some concluding thoughts. So the ergon method, this is something if you Google around, you're not going to find because it hasn't been published yet. It's something we're working on here at the lab. Essentially, as you could tell, up until this point, it's been a lot of build your own adventure, trying to reverse engineer 0711 to design tasks that will get you to a successful disposition. Ergon is a method we're proposing that instead is something you can follow that should assure you of 0711 success as long as you follow it. We're hoping that this can help make nuclear design a little bit easier, simpler, and help bring around more innovation. That's been a problem. It's hard to innovate when you're not sure if you will be able to even implement your design. Keep in mind the methods and measures is what that's supposed to say, not measured. In reality, you use specific methods to gather specific results or measures. So this is where you'll see formative and summative for the first time. Depends on where you are in the design process on how the methods and measures will tend to manifest themselves. Formative is when the design is still being formed, it's early stages. Summative is the design's complete, it is now being validated. Those are really common conceptions in nuclear. So another thing to keep in mind, why would you use different methods and measures depending on where you are in the design phase? Early on, it may be important to know why they didn't do well or didn't like it. Qualitative feedback actually is more helpful than steps. Let me see here. Okay, sorry about that. If you heard a little squawk, I almost was faster than the toddler when she ran in here to talk to me. So yeah, we're more interested in why they didn't do well. So this example is really, really prescient of things that will happen during your operator studies. I didn't understand the dialog box and clicked the wrong button is way more helpful than, hey, some of these people clicked the wrong button. But later on, it's important to know how they did to pass the design ISV and verification validation tasks. At that point, you should know why, is I think some of the expectations there. If you've done your iterations well and you've done your user testing well, most of your findings will be settled by the time you get to the end. Here we go. GoNuke, this is an example of a process that was developed here at the INL by Dr. Ron Boring. So this is one of those examples where we're trying to fit 0711 into a design life cycle. Again, if we do this and we can check off every box, it helps us when we get to the end to show that we really did do everything that 0711 asked of us. It's primarily an evaluation framework and designed to help guide you with which type of evaluation is most useful or relevant at whatever place you are in your design step. So you have your evaluation phase up here. This is kind of, think of it chronologically, and then the various types that you'll undergo at each step. And there's your ISV there. So in summary, human factors gathers knowledge and applies it to inform the design of the system. Various human factors methods are suited for gathering specific pieces of knowledge required for the design. So it's important here to remember is each of these steps, when we go back here, it has a key part of the design. There's a reason that we do it. And a big reason you have to do multiple types of evaluation is essentially looking at an aspect like a triangulation. You know, if you can catch 60% of issues with any one evaluation tool, well, the more that you do, the more you're going to catch. And you might need different angles to catch those problems. So that's really, really important to make sure that you didn't just do one type of evaluation the whole way, because you will have undoubtedly missed some issues that you could have fixed earlier. Okay, now we're going to stop there. and I will do this on the next lecture, which will be shortly. Let's see here. And thank you.